Hi, and welcome to this lecture on the matrix elements of Slater determinants in the series of advanced quantum mechanics. In this lecture I will calculate the matrix elements of operators between Slater determinants. The purpose of this is to, in the end, be able to compute the energy associated with a particular Slater determinant, but we will keep it more general and initially look at just arbitrary operators. But to keep it more simple, I will focus on a 2-electron system, derive results for that case, and then afterwards I will generalize to an n-electron system. So what we are talking about here is a 2-electron system for which we might have a Slater determinant such as this one, and let me put up another one which I will be giving primes. So these two Slater determinants are generally different, but the functions here and here are taken from the same set. So they are eigenfunctions of the same operator. So what I mean here is that phi I prime is really just another one from the set. So it's another way of writing psi, and then you could say I prime. So it's just a different index. And these are, of course, orthogonal. So phi I prime here is a delta. And if there are some identities here, if some of those orbitals, let's say the first one here and here, are the same, so that these two rows are actually identical, then we will definitely assume that those orbitals are in the same column or in the same row. What I mean by this is that there is no chance that this 2 prime is in fact identical to phi 1. If there's an orbital over here, which we also find over here, then they are definitely in the same row. We will arrange things like this. So we can make sure that phi 1 is always orthogonal to phi 2 prime, always. All right. The operator we are talking about, I will denote as F. And it operates on both electrons, and it's symmetric. So it doesn't depend on the ordering of the electrons. So what I would like to compute is this particular matrix element. So let me write up what we have here. Well, let me write out the first determinant. So I get a 1, 1, 2, 2, minus 2, 1, 1, 2, all of this conjugate, F operator, and then the other determinant I might just keep as a determinant. These integrations here denote the fact that for each electron we have to integrate over all spatial coordinates, but also over the spin degree of freedom. So that's why it's symbolically written as a 4-dimensional integral. Now what we see here is that there are, if we focus on this minus here, there are 2 terms here. One with 1, 1, 2, 2, and then the other one here where the arguments are interchanged. So what I could do is, since these are just integration variables, I could interchange here. I'm allowed to do that. I'm also allowed to do that over here because it's a symmetric operator. But if I do it here in the determinant, so I here get an argument 2 and here I get an argument 1. This actually means that I flip the sign of the determinant, and that will cancel this minus sign. So what I actually find here is that the two terms, from the one from this part and the one from this part, are in fact identical. So that will cancel this factor of 2 here, and I get just the first term, and then my operator, and then the second term here. Right. So this is our starting point. And now we will try to look at different cases. The first case will be the one where F is a sum of one electron operators, and the second important case is where this F is truly a 2 electron operator. So the first case I'll denote by A. So in this case F is given in this manner. So it's a sum of 2 identical terms, one for each electron. So I have to plug that in here. Oh, just forgot the conjugations here. Put those. So here I'll get F of 1 and F with the argument 2, and then the second slated determinant, which, let's write that one out also. So here I get 1 prime 1, 2 prime 2 minus 2 prime 1, 1 prime 2. Now we can look at the first term here, the one involving F with the argument 1. So there's an integral over the coordinates of the first electron. So that involves this function, and of course this operator, and then we have this function here. But then I have, in this integral, again, I have this one times this one. And that might be 1 if 2 prime is actually the same as 2. Otherwise, of course, it's 0. Then I can look at this term coming from that part over here, where I have a 2, and then this operator which has nothing to do with 2, and then this one. And that is definitely 0, because this orbital is definitely orthogonal to this one. So that can never give me anything. And of course, similarly, if I take this term with this operator, then this term might give me something if 1 is the same as 1 prime, but I'm sure that this term with this one will give me 0. So what I can say is, in fact, that there are 3 possible cases. The first is the one where the 2 stated determinants are actually equal. So 1 prime is the same as 1, and 2 prime is the same as 2. Then there's a second case where there's one difference between the 2. So I might say that, let's say that only phi 2 prime differs from 2. Right? So obviously 1 prime equals 1. And then there's the final case where both of them are different. For reference to what we'll do later, I will write it as more than one difference. Okay, in the first case, so now in the first case I'll forget about the primes. So I have this one with this operator and this guy here, and then I have 2 with 2. So the 2 integral in this case just gives me 1, and what's left is this with this and this, which is just 1 if 1. And as I argued, the term which gives me with this one and this one and this guy over here is definitely 0. Then there are the terms corresponding to this operator. So I have this guy times this one times this. Again, the 1 integrals here will give me 1 because they are normalized, and I get here 2f2. And then there's the final term, this guy, and this guy, but that's also definitely 0 because the 1 orbitals are orthogonal. Right. Let's assume now that 2 prime is actually different from 2. So it might be that 2 prime is really 3 or 7 or whatever. And they are, of course, orthogonal. So now if I look at this first term here, this one with this operator and this guy, that would give me something. But now I would have 2 up against 2 prime, and they are now orthogonal. So this term which I had here will actually be 0 because of the orthogonality here. So the only term I'm left with is this one, which now reads like this, right? So if 2 and 2 prime are actually different, this is the only term that survives. And then obviously, if there's more than one difference, so if both of them are different, then I will get 0, because the operator here can only save the integral for one of them if they are orthogonal. So for instance, if those 2 are orthogonal, this integral over 2 will give me 0. If I look at this term, then it might be that those 2, the 2 integral in this case could give me something that's not 0, but then the 1 integral would be 0. So I get in total a 0 there. Right. So that was the A case. Then there's a B case, and you guessed it, f in this case is some G operator, I could call it, which now really depends on both arguments, and it's symmetric. So this is also this guy here. And the only thing we can say is that I will get 2 terms. So I get a term analogous to this part times my operator, which is now this, and then this term. And I will write that as phi 1, phi 2, g, and here phi 1 prime, phi 2 prime. And then there's the second term with the minus, phi 1, phi 2, g, phi 2 prime, phi 1 prime. And what I mean by this notation here in general is that, write it here, A, B, and then this 2-body operator, C, D in general is just a shorthand for a double integral phi A conjugate with the argument 1, phi B conjugate with argument 2, the operator, and then a C with argument 1, D with argument 2. That's it. Right, so the important point here is that the first 2 operators have the same argument, the first 2 functions have the same argument, and the second functions here have also the same, but different, of course, argument. So 1, 1 and 2, 2. Right. That is as far as we can get in the two-body case, two-electron case. Now we will try to generalize this to the case where there might be actually n electrons. So let me switch the blackboards. So we now assume that we have n electrons rather than 2. And then we will try to generalize. We'll start by looking at the A case. So now my F is simply a sum here of some symmetrical one-body terms. And if I generalize what I just did, what I find is that the matrix element here, again, there are three cases. Again, the first one is that the two stated determinants are actually equal. The second case could be that there's one difference, so let's say only phi k prime differs from k, and then the third case is that there's more, again, than one difference between the two. In the two-body case, we had a matrix element for each electron, and of course we get the same here, but generalized in this manner. So let's say k, phi k, f, and phi k. So we simply get a sum over single-body terms, one for each orbital. Now in this case here, if there's a difference in one place between the two stated determinants, this means that these two orbitals are orthogonal. So if they're just multiplied together and integrated over, we get a 0. So it means that it has to be an element which includes the operator to lift this orthogonality. So the only term that will survive here is actually this one. Because if F does not operate on K prime, so it operates on one of the other orbitals, then the orthogonality between K and K prime will make sure that that term is 0. So F must operate on K prime, so this is the only term that will survive. And then, of course, I still have a 0 here if there are more than two differences, because this operator can only save me in one spot. Right? It's a one-body operator, so if there are more than one orthogonality in my set, then this will definitely be 0. So that is the A case. Then we have the B case, the two-body case. So now my F is a sum over all pairs here, G, which now depends on two coordinates. And now, in fact, I have 4 possible cases. First, again, is that the two are identical. And there is again a second case where precisely K prime differs from K, but that is the only difference. But now I only have a case that is this one, where I have precisely two differences between the two orbitals, and then I have a fourth case in which there's more than two differences. So the story obviously is very much like we had for the one-body case. These orbitals might be orthogonal, but if they're in a matrix element such as this one, including the operator, that will save the orthogonality, so that matrix element might actually be non-zero, but it requires the operator. If I just have an element like this. It is of course 0 if the orbitals are orthogonal. So in the first case here, all orbitals are identical, so all terms will survive. And if I generalize what I had for the two-body case, what I get is simply a big sum here. I get the K, L, G, K, L term, and then K, L, G, L, K term. So they all matter here because no orbitals are orthogonal, so whatever is outside here, there's a bunch of ones that came from the integrals over all the other orbitals, but they are all ones. Now, in this case here, now that we have precisely one difference, then this orbital must be in here. Otherwise, we get a 0. On the other hand, the other index, the L index, can be anything. So what I get here is a single sum over L. I get a phi K, phi L, G, and here K prime L, and here a K, L, G, L, K prime, like this, right? So the K must be inside my sum here. So remember here, of course, K is some definite number. Here K is just a summation index. Here K is something very definite, and it must be included, otherwise I get a 0 from all the terms outside here. On the other hand, the other orbital in the pair here can be anything. So that's what I get. And then of course it's easy to imagine what you have in the final, or in this case here. If you have two orthogonalities, then there's no free summation. Both of them have to be inside an element like this with a G operator to save the orthogonality. So there's only a single term surviving in that particular case. K prime, L prime, K L, G, L prime, K prime. That's the only surviving term. If any of those two, K and L, are not operated on by the G operator here, we will get a 0 due to orthogonality. And then of course you can imagine that down here I will obviously get 0, because if there are more than two different orbitals in my Slater determinants, then this two-body operator cannot save things anymore. There will be at least one term here which is 0. So this is what I get. In terms of names, this first integral here might be called a direct one. So that's the one where we don't flip anything, don't exchange anything. So K is with K, L with L. Whereas this one over here, where we interchange on the right-hand side, this is an example of what is called an exchange term, which is very, very important. We'll talk about it a lot in later lectures. But here you see that it's called exchange because we exchanged the two orbitals, or if you like, the two electrons here on the right-hand side. So now what I want to do is apply this to the energy operator, to the Hamiltonian, in order to be able to calculate the energy of a Slater determinant. The expectation value, if you like. So now my operator is not some arbitrary F, it's my Hamiltonian, which contains a bunch of single body terms. So that's first part is similar to the A case, but then of course there's also a bunch of two-body terms which look like this. So it's a mix of an A part and a B part. The nice thing here is that the B part is actually not a real operator. This is just a function, so it doesn't operate on anything, it just multiplies And this means that we don't have to worry about the order of terms when we talk about this factor here. Of course, with the first part here, we need to be very careful with the ordering. To make it simple, let's just look at the case where the two stated determinants are the same. So that is exactly the expectation value of the energy between the states there. And now I will apply my results from up here. So I first have the contribution from the single body part, and that just gives me sum over phi I, and then my H single body operator phi I. And then there's the second part here. We get a sum over all pairs phi I j 1 over R12, and then phi I phi j minus the exchange term I j 1 over R12 j I. So in this last part, the orbitals are exchanged over here. And the notation here, of course, means that the first orbital has the argument R1, the second one has, the one in the second place here has the argument R2, right? And this is the distance between those two arguments. So let's again introduce some notation. This is the single body part, and for now I will call this integral hi and then a prime. Now this prime has a different meaning from what we just used, but I will explain in a minute. Then this two-body integral I will call j ij and with a prime as well, and then there's the final one here, which is called k I j prime. And now these three primes here, they mean that at this stage we haven't performed the spin integrations in here. Here is actually a four-dimensional integration, three spatial ones and one spin integration. Here and here we have 8 integrals, 6 spatial ones and 2 spin integrations. So that's what the prime means. So let me write that. That this prime means before spin integration. And of course, as you can guess, when I remove the prime, it means that now the spin integrations have been performed, only the spatial integrations are left. And spin integration sounds fancy, but it is very simple. It's just looking at the two orbitals, in this case for instance, and then if the two spin parts here are the same, I get a 1 from spin integration. If they're different, I get 0. That's what it is. And of course, in this case, it's one orbital with itself. And of course, this orbital will then have the same spin part as this one. It's an identical orbital. So obviously, this does not depend on spin, right? The spin part here and here must be the same. So I will just do like this. So there's the spin integration in this case will always give me 1. The same is actually true for the Coulomb integral, as this is called. Let me also write that this is Coulomb integral, and this is in the exchange integral. In this Coulomb part, I have phi I with phi I. So again, identical orbitals with identical argument. So when I do the spin integral over this argument, I obviously always will get a 1. And the same for this one. So for the Coulomb integral, it's just a simple spin integration will always give me 1. But for the exchange part, things are a little more tricky. Because now I exchanged orbitals over here. And the spin part of phi I is not necessarily the same as the spin part of phi j. If it's 0 here, of course it's also 0 here, and everything is 0. If it's 1 here, Sorry, ran out of recording time, so let me just repeat the last little bit here. What we were talking about was this exchange term here. So there's the orbital phi I against j, and here j against I. And the point is that if this element is going to give me anything that's not zero, then the spin part of I and j must definitely be the same. Otherwise, spin orthogonality will give me 0. But if those two orbitals have the same spin, then those two also have the same spin, they're the same orbitals, and then the spin integration simply gives me 1. So what I end up with in this case is what I wrote here, that I have the spatial part. So again, that's what it means when there's no prime here. It means that I still have to do the spatial integrations. And then there's this delta, which tells me that I only get an exchange term if the two orbitals have the same spin. So exchange only acts between electrons with identical spin. So the two spins must either be up or down. If I have an up against a down, there is no exchange interaction. This is in fact the reason why ferromagnets tend to align their spins. It's because they gain some energy due to this minus here coming from the exchange interaction. But now we will try and apply this to something much simpler, our beloved helium atom. So let me switch blackboards once again. So the helium atom is a two-body case, obviously. And we can start by looking at the ground state, for which my Slater determinant is constructed of two 1s orbitals, spatial orbitals, one having spin up and the other one having spin down. So now I would like to calculate the expectation value in this case, and my recipe tells me, let me reproduce that here, that generally I should sum over all the single body parts, and I don't have to put the prime because I have already done the spin integrations. Then I have a sum over all pairs of electrons. Sorry, there's the Coulomb part, which I always get irrespective of spin. And then there's the exchange part here, which I only get if the two orbitals in question here have the same spin. So this is what I want to apply to the helium case. So these are my two orbitals, and obviously they have different spins. So first I have the sum over single body contributions. Both of them are 1s cases, 1s states. So here I get 2 times H 1s. Then I have a single pair here. It's only a single pair in this two-body case. So I get a single Coulomb term, which is J 1s, 1s. So that's the Coulomb interaction between one electron in a 1s state and another electron in a 1s state. And that's all, because since they have different spin, there is no exchange interaction in this case. So that is very simple. But let's now go to the different excited states. As we already discussed earlier, there are 4 possible excited states if we look at the 1s, 2s manifold. Because in this case, there are no spin restrictions. So one possibility is that I look at a 1s plus 2s plus. This is a possible excited state. It belongs to the triplet because the net spin projection here is 1, but the two spatial parts are different. It's a 1s and a 2s. So what I get in this case is, well, I have a one body part here, that's H1s. I have one here, which is H2s. Then I have my Coulomb interaction between the two electrons, which I will denote 1s, 2s. And now in this case, I actually do get an exchange interaction because I have identical spin, so I get a minus K1s, 2s. And you might wonder about the sign of K itself, but it can easily be shown by Fourier analysis that K, in fact, itself is always positive. So this minus means that it actually reduces energy. So that's easy. That's what I get in this case. But what about the other three excited states? We know that there's a minus part in the triplet that obviously gives me exactly the same. But then we have the two excited states with zero projection. So let me call those psi plus and minus. And we know that actually those are not just individual Slater determinants, but they are linear combinations. So it's a 1s plus with a 2s minus, plus or minus a 1s minus with a 2s plus. And the plus part here is the one that goes with the triplet. So that's the one that's associated with this state. And the minus one is the single one belonging to the singlet. So the minus state here is the one which has a spin of magnitude 0 and projection 0. So now I want to compute the expectation value for those states. And that is, of course, a little more tricky. Let's start here. First, I have this part with itself. So I get 1/2 here, and this part with itself, that is the same recipe as we have used already, the same Slater determinant on both sides. So in this case, I get an H1s and an H2s and a J1s, 2s, the Coulomb interaction, but no exchange term because the spins are different. Then there's this part over here. It's the same but with opposite spin, but since spins don't actually contribute here, this part will give me exactly the same. When I take it with itself, the minus sign will be squared. Right? So I just get this part twice. But then I have the cross term, this on the left-hand side with this one on the right-hand side, and the analogous term here. So I get a plus minus 2, and then a matrix element of this form. Here's the Hamiltonian, and here's the 1s minus and 2s plus. So this is a new kind of matrix element because now I have different Slater determinants on left and right hand sides. So I have to apply the general rules that I used before, whereas those, the ones I have here and here, they're simple ones because in those cases I had the same Slater determinant to the left and the right. Now obviously I have different ones. Right. And what I already did here was group the two and see that they're the same. Right? The other term would just be with a minus plus spins flipped, but that does not matter. So I just multiplied by 2 here. So if I look at this term here, what I notice is that when I compare left and right hand sides, there are actually two differences, right? There's a difference here, and there's also a difference here. There are only 2 orbitals in the system, in the Slater determinants, but they're actually both different. So there are no identities. So this means that when I think back to the cases I looked at already, the single body part of the Hamiltonian will give me 0, because as you might remember, if there's more than one difference in this matrix element for a single body operator, then I will get 0. On the other hand, for the 2-body part of H, I do get a contribution. So I get, let's write it like this. I get a 1s plus and a 2s minus, and then the operator, which is 1 over R12, against a 1s minus and a 2s plus. That's the direct term, and then I get a minus 1s plus 2s minus 1 over R12, and then in this exchange term I have to flip here, so I get a 2s plus and a 1s minus. So that's what all of this is. And now I have to inspect these elements. In the first one here, I have this orbital times this orbital with the same argument, and then this times this with another but same argument. And that is going to give me 0, because here I have a plus against the minus. So spin orthogonality here, and in fact also here, gives me 0. So this term in itself here is actually 0. This one over here, in contrast, is not 0, because when I flip the right hand side, I now get, sorry, I was wrong here, let me write it the right way. It should be 2s, 1s. Here I get a plus against plus, and here a minus against minus. So in this case, actually spin integration is going to give me 1. But then I get a 1s times a 2s from this part, and the other one is actually the same. So this integral is precisely the spatial part of the exchange interaction, exactly the same as the one I had over here. So this integral is precisely k1s 2s. So what I can say by summing up all of this is that the E plus minus, they're going to give me the single body part, H1s, 2s, and the Coulomb part, 1s, 2s, and then I get a plus minus, and this one is going to give me 0, and then this final factor here. So actually plus minus becomes minus plus k1s 2s. That's it. So again, the minus, the top sign is what goes with the triplet, the lower sign is what goes with the singlet. So I see that actually my triplet result is precisely identical to what I had over here. And then this is exactly what we were hoping for, that the 3 states of the triplet should have identical energies. And we see that this is indeed the case. The energy of the triplet is 1s plus 2s plus the Coulomb minus the exchange. On the other hand, I find that the singlet energy becomes 1s, 2s, 1s, 2s plus k1s, 2s. So the singlet, the excited singlet there is actually at higher energy than the excited triplet. So I can finish by drawing an energy diagram. The ground state here is the 1s2 state, and this is of course a singlet, they have opposite spin. But then the first excited state, so I have 2 excited states in this, in the 1s, 2s manifold. I have the lowest one, which is the 1s, 2s triplet, and I have the upper excited state, which is the 1s, 2s singlet. And this interval here will then be the difference between those two here. So one of these will cancel, so I get 2s minus 1s. Or maybe we can talk about this bit here going to the center between the two, because then this is 2s minus 1s, and then in this case I get just this Coulomb term minus this Coulomb term. The one is 2s minus 1s 1s. So those are approximately the same. So the major part of this excitation energy is the single body part, the cost that you have to pay when you excite an electron from 1s to 2s. But then these also split. And the split, the resulting split, is precisely twice the exchange interaction, because the triplet with the minus here is pulled down by one exchange integral, and the singlet is pulled up by the same amount. So the splitting is 2 times this. So actually the lowest of the excited states is the triplet, and the singlet there is the highest one. And in terms of actual numbers, this splitting here is something on the order of 21 eV, and this is something on the order of 2 eV, right? So there's an order of magnitude difference between the 2 splits there. So that's what it looks like in our dear helium atom. Right, so let me finish off by going back to my blackboard over here. Just a sec. There we are. What we have done here is write the expectation value of the energy when we approximate our state by a Slater determinant. And as you can see, it of course depends on the building blocks of the Slater determinant. All these single body orbitals that enter here, 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 and everywhere, right? So once we specify the Slater determinant, obviously we can compute this energy. And the goal is to find the best possible Slater determinant such that this energy is as low as possible, because we want to get as close to the real ground state as possible. So we want to find a Slater determinant which is a very good approximation to the actual ground state. And now what we have found is that this energy is actually a functional of these building blocks, the single body spin orbitals that go into the Slater determinant. And now what we have to do is vary them. We have to find the best single body operators, and we do this by this functional analysis, where we take the functional derivative of the energy here with respect to these orbitals, and then we set that functional derivative equal to 0 and solve, and it turns out that again this will provide a set of coupled differential equations. They're known as the Hartree-Fock equations. This is known as the Hartree-Fock method. And you have to solve these coupled differential equations, and there's a lot of technicality in there that you will learn about. There's also the fact that you have to worry about normalization of these orbitals. And that is another tricky part, where you have to add a Lagrange multiplier, ensuring that your orbitals are actually orthogonal. But all of that will be clear to you in coming lectures. Bye there.